One of the questions that I often get asked by pupils is, "Sir, does spelling matter in chemistry?" Now, the simple answer is yes, of course spelling matters. Spelling matters in all subjects. But keep listening for a little bit more of a detailed, nuanced answer. I'm Mr. Lee, and welcome to another episode of Chemistry Revision Stories. Before we get started, I realised I made a little bit of a slip of the tongue when I was going over the summary of the Group 1 reactivity in the last episode. I accidentally said that the universal indicator turns cloudy when the Group 1 metals react with water, but of course it goes purple. So apologies for that little mistake there. Before we start, we've got last week's homework questions to have a look at. The first question was, what gas do Group 1 metals release when they react with water? And the answer was hydrogen gas. The next question was, what type of solution do they produce? And they produce a hydroxide solution, which is alkaline, hence why they're called the alkali metals. And the last question was, why does the reactivity of Group 1 increase? Remember, the outer electron is getting further away from the nucleus, so it's less attracted to the nucleus as you go down the group, and therefore it's more easily lost. Well done if you got all three of those questions correct. Today, we're going to be looking at the reactivity of Group 7. Unlike with the reactivity of Group 1, we don't have a single element that we can easily react our Group 7 with and just observe how vigorous the reaction is. So we have to use a slightly different method. And the method that we use is using displacement reactions. To help you understand displacement reactions, our story today starts at the disco. But not just any old disco, it starts at the displacement disco. So at the displacement disco, we have got Peter Potassium. And Peter Potassium is dancing with Cindy Chlorine. They're having a good old boogie. But along comes Phoebe Fluorine. And Phoebe Fluorine challenges Cindy Chlorine to a bit of a dance-off. So they have this dance-off, and Phoebe Fluorine is a much more reactive dancer compared to Cindy Chlorine. So what happens is, during this dance-off as they're boogieing away, Phoebe Fluorine bumps Cindy Chlorine out the way. And so Phoebe Fluorine is ended up dancing with Peter Potassium, and Cindy Chlorine has been displaced. This is a story that I like to use to show what happens in a displacement reaction. You've got two elements that are in solution, dancing together. In this case, it was the potassium and the chlorine. And then you introduce a third element, which was our Phoebe Fluorine. And because the Phoebe Fluorine was more reactive than the chlorine, it was able to displace the chlorine. And so the less reactive element, the chlorine, was left by itself. To think about this from a more chemistry point of view, imagine you have got a solution of potassium chloride. In that solution, there are potassium ions, and then there are the chloride ions, and they're floating around. They're in solution. And then we are adding an element. We're adding fluorine. And when we add that fluorine into the solution, the fluorine displaces those chloride ions. And so the fluorine moves into the solution and becomes fluoride. And the chlorine moves out of solution and becomes chlorine. The potassium hasn't changed at all. Those potassium ions remain unchanged. And so we call them spectator ions because they haven't been involved in the reaction really. They've just sat there and watched the change as the fluorine becomes fluoride and the chloride becomes chlorine. This is where our spelling becomes really, really important. If we were to write a word equation for this reaction, we would have potassium chloride plus fluorine, and we make potassium fluoride plus chlorine. So you can see there the end of the word changes. When it is in solution with the potassium, our group 7 elements end in ide, I-D-E. When they are by themselves as an element, they end in ene, I-N-E. So that single letter difference, the N and the D, changes the meaning of the word, because the "ide" means it's an ion and it's in solution with the potassium. So where does the nuance come in with these spellings? Well, in an exam question, if you spelt fluorine, but you got the U and the O of fluorine mixed up, you wouldn't lose a mark for that. Just like if you missed out the double S for potassium and you only put one S, you wouldn't lose a mark for that. But if you write an N when it should be a D, if you write "een" when it should be "ide," or "ide" when it should be "een," then that will lose you a mark. So you need to be really, really careful with the spellings of our chemicals, especially the ending of them. Before we delve into the trend in the reactivity going down group 7, it's time for the element of the episode, which this week is chlorine. Chlorine's atomic number is 17 and its atomic mass is 35.5, which might seem a little bit odd at first, given that we can't have half a neutron. So how do we get this 35.5 as its relative atomic mass? Well, it's a really good illustration that elements can have different isotopes in different abundances. In this case, chlorine has two isotopes, one with a mass of 35 and the other one with a mass of 37, but they don't have the same abundance. If we look at a typical sample of chlorine, about 25% of it will be chlorine 37 and about 75% of it will be chlorine 35, which shifts the relative atomic mass overall closer to the 35, and that's how we get a relative atomic mass of 35.5. Although chlorine is actually quite a toxic gas, and it's actually one of the elements in mustard gas that was used back in World War I as a weapon, it's actually got quite a few uses in our everyday lives. For example, they add a little bit of chlorine to drinking water. They also add a bit more chlorine to swimming pool water, and they both do the same job, and that's to kill any harmful bacteria that might infect us and make us ill. Like most things in life, too much of something can be very bad, but in the right quantities, it can actually be pretty useful. Let's look at the trend in reactivity now of group 7. When we do these displacement reactions, reacting fluorine with potassium chloride, potassium bromide, potassium iodide, etc., what we find is that the elements at the top of group 7 is able to displace everything below it. So fluorine is able to displace all of the other group 7 elements. Chlorine can only displace what is below it, so that's bromine, iodine, astatine. Bromine can only displace what's below it, so that will be iodine and astatine. And iodine will only be able to displace astatine. And remember, because the more reactive element displaces the less reactive element, this tells us that as we go down group 7, the reactivity of group 7 is decreasing. It's becoming less reactive. And we can observe this from the displacement reactions, because when we add chlorine to potassium bromide, as the bromide is kicked out of solution as it's displaced and becomes bromine, we see the orange colour of bromine being formed. The same thing with iodine. As the iodide ions are displaced, we see the brown colour of iodine. Just like with group 1, you need to be able to explain the reactivity of group 7 as we go down. So we need to know why it becomes less reactive. And we can use exactly the same ideas that we used to explain the reactivity of group 1. Each time we move down an element in group 7, we add an additional electron shell. So the outer shell is getting further away from the nucleus as we move down the group. In addition, there are more other electrons between the positive nucleus and that outer electron shell. And those extra electrons have a shielding effect on that outer shell. Imagine them sort of competing for the attraction of the nucleus. These two factors, the outer electron shell being further away and the electron shielding, mean that the outer shell is less attracted to the nucleus as you move down the group. Now that part of the explanation is identical to group 1, but here's where it changes. With group 7, they have 7 electrons in the outer shell, And when they react to form an ion, they gain one electron. And so if these elements are trying to gain an electron and the attraction between the nucleus and the outer shell is getting weaker as we go down, it's going to get harder and harder and harder for these atoms to be able to gain that electron when they react. Therefore, the reactivity decreases. Let's sum up the key points you need to know about group 7. In a displacement reaction, the more reactive element is able to displace the less reactive element, and the less reactive element becomes visible. In group 7, the elements at the top of the group can displace everything below it. This tells us the reactivity of group 7 decreases down the group. You need to be really careful with your spellings when you're writing these word equations. When the group 7 element is in solution with something like potassium or sodium, it will be an ion, and so it needs to be "-ide", for example, fluoride. When the element is in its element form by itself, if it's been displaced out of solution, we need to have "-ine", for example, chlorine. And finally, the explanation of reactivity. As we go down the group, the outer electron shell is getting further away from the nucleus. There's more electron shielding. Therefore, these elements find it harder to gain an electron because the attraction between the outer shell and the nucleus is a lot weaker. Before I go, I'm going to leave you with 3 more homework questions. Question number 1. What element would be able to displace chlorine? Question 2. What would the products be when chlorine reacts with sodium bromide? And question number 3. Why do group 7 elements get less reactive as you move down the group? To find out the answers to those questions and to delve into some more key chemistry concepts, join me for the next episode of Chemistry Revision Stories. Thank you very much for listening. See you next time.